Now that we're discussing graphs, we can also go for a walk. So if we have a graph and the vertex set is called V and the edge set is called E, a walk is an alternating sequence of vertices and edges, starting with a vertex. So you start with a vertex, and we usually index it as V sub 0. After a vertex comes an edge, E sub 0. After an edge comes a vertex, V sub 1. After a vertex comes an edge, E sub 1. V2, E2, V3, E3, and so forth. It's perfectly acceptable for a walk to end. If the walk does end, it also has to end with a vertex. So it's possible to have a walk of infinite length, in which case you start with a vertex and then you just alternate vertex, edge, and so forth. If you want to end it, you must also end with a vertex. In which case, you see here that we start with a vertex, edge, end with a vertex. In both cases, whether the walk is infinite or not, the edges that are in your walk must connect the two vertices in between them. So in the one written above, edge E sub 0 has to connect this vertex and this vertex. Edge E sub 1 must connect V1 and V2. All the way until you get up to this last edge must connect these last two vertices. So it's not just a random assortment of vertices and edges. From one vertex, you take an edge which leads you to another vertex, and so forth. So a walk represents a sort of way of starting at one vertex, following an edge to another vertex, from which you take an edge to another vertex, and so forth. So for the following graph, here we have it. Here is a perfectly valid walk. This tells me I start on A, so we start here. Then I take the edge connecting A and B. Now I am at the vertex B. Then I take the edge connecting B to B. Now I am at the vertex B. Then I take the edge which takes me from B to D. Now I'm at the vertex D. I take the edge from D to C. And now I'm at the vertex C, and then the walk ends. This, however, is not a valid walk, so can you spot what the problem is? In this walk, this vertex is not the end of this edge. It's also not the start of this edge. If I tried to do this walk, I would say start at A, from A go to B, and now you're at D. No, I'm not. And we have a problem. Now, if the graph is directed, the direction of the edges must be respected in the path. So if a graph points in a given direction, you are only allowed to walk along it in that direction. We also have things like trails, paths, and cycles. So if you have a walk on a graph that does not ever repeat an edge, that's called a trail. If you have a walk on a graph that does not repeat any vertices, except perhaps ending where it started, that's called a path. So a trail does not repeat any edges. A path does not repeat any vertices, except maybe ending where it began. If you have a walk on a graph which ends at the same vertex it began, that's called a cycle, so it comes back to where it started. If a cycle is a trail, in other words, does not repeat any edges, and is also a path, in other words, does not repeat any vertices except coming back to where it started, it's called a simple cycle. So a simple cycle comes back to where it started without ever having repeated any edges or vertices except for the fact that it did come back to where it started. In a simple graph, remember that at most one edge can connect two vertices. Because there's only a single edge connecting two vertices, the edges are sort of redundant in listing out your walk. You simply list out the sequence of vertices saying walk from one vertex to the next, on the assumption that there is an edge connecting two consecutive vertices in your list. But a multigraph might have multiple edges connecting two given vertices, in which case you need to keep track of which edges have been used. So then in a multigraph, you really do need to list out your edges as well. We also want to discuss something called a connected graph. So a graph is going to be called connected if whenever you pick two vertices, it is possible to walk from one to the other. And we do keep track of where that walk starts and stops. And technically, we need to account for the possibility that we picked the same vertex twice. In other words, if I pick a vertex from the graph, I need to start a walk there and end the walk there. But that's always doable. Okay? A walk was actually not obligated to contain any edges. So if you pull a vertex, you can simply state, there's my walk. Start at that vertex and do nothing. In a directed graph, however, we do need to keep track of both directions. Okay? Starting at v1 and going to v2 could be a very different walk than starting at v2 and going to v1, because not every edge can be followed in both directions. So in a directed graph, it's very important to know where you're starting versus where you're finishing. But in an undirected graph, since edges can be traversed in both directions, it's not really such a big deal. If you can get from v1 to v2 in an undirected graph, you can simply take the walk backwards to go from v2 to v1. In directed graphs, what you might have is that for any pair of vertices, there's a path in one of the directions, but not necessarily both. That's called weakly connected. If, however, for any pair of vertices there is a path in both directions, the graph is called strongly connected. For undirected graphs, this doesn't mean anything. Remember, for an undirected graph, a walk that can be done in one direction can always be done in the other. So we would just say connected versus not. But for a directed graph, it's possible that certain pairs of vertices can only be connected in one direction and not the other. So we have this distinction. Weakly connected means for any pair, there's at least one path in one direction. Strongly connected means for any pair of vertices, you can actually achieve the walk in both directions. For small graphs that are represented visually, usually you can just look at it and tell if it's connected, versus disconnected is the term for a graph that is not connected. But if you have a very large graph, or maybe a graph that's only stored in a computer and it's not actually represented visually, this abstract definition is important. A connected graph is one where any two vertices can be connected with a walk. With a directed graph, if the walk can be done in both directions, it's called strongly connected. If only one direction, it might be called weakly connected. Okay, the next slide, we're going to see examples of both of these concepts. Here are these examples of connected and disconnected graphs. Here is a connected, undirected graph. Can I get from vertex 1 to 2? Yes. From 1 to 3? Yes, by doing a walk that goes through vertex 2. From 1 to 4 is one step. From 1 to 5 is one step. 2 to 3, 2 to 4. Can I get from 2 to 5? There's actually multiple ways to do it. I can go like this, or I could do that, etc. Any pair of vertices you pick, it's totally possible to walk from one to the other. Here is a strongly connected directed graph. So it's directed, all of the edges have a direction, and I claim it's strongly connected. Can I get from vertex 5 to vertex 2? Yes, by doing this walk right there. Can I get from vertex 2 to vertex 5? Yes, by going around like that. Okay. So any pair of vertices you pick, 2 to 4 or 4 to 2, I can do both directions of that walk. I can get from vertex A to vertex B or vertex B to vertex A while still respecting the directions of the arrows. That's strongly connected. Here, however, is a weakly connected graph. Can I get from vertex 1 to vertex 2? Absolutely. Just take that path. Can I get from vertex 2 to vertex 1? No. Once I'm at vertex 2, the only place I can go is vertex 3. And now I'm sort of stuck over here. If I'm at vertex 2, I'm never going to be able to get back to vertex 1. This is weakly connected. It's possible to find a pair of vertices where there is a path in one direction, but not the other. This, however, is just a disconnected graph. And visually, we just see, yeah, there's two pieces to it with no connection between them. There is no walk, for example, from vertex 2 to vertex 3. This is a disconnected graph. Continuing with our talk on graph theory, there's a notion of deletion. Given a graph, vertices v, edges e, we can remove items from the graph to make a new, smaller subgraph. Okay, given any edge, if you keep all the same vertices, but you simply replace the edge set with this difference, in other words, from the set E, you take out that single edge, that's what's being called deleting that edge from a graph. Alternately, you can replace the vertex set with a new one by removing a single vertex. But if you've removed a vertex, in order to have a legitimate subgraph, you also have to delete every edge connected to that vertex, because otherwise we'd have edges that don't connect to anything. For example, here's a graph. We can delete a single edge. Okay. So here's the graph, and I simply delete the edge connecting C and F. Fine, no problem. We did, however, go from a connected graph to a disconnected graph. Deleting edges can understandably change properties of the graph. But what would happen if I tried to delete the vertex D? So here's the original graph. If I simply delete the vertex D, now we have some edges that don't make sense. So we have to also delete all the edges that used to connect to the vertex we just removed. So this would be the graph accomplished by deleting the vertex D. So deleting an edge, very straightforward. Deleting a vertex also requires you to delete the edges connected to that vertex. But this is a way of making subgraphs. So here's a result, our first theorem about graphs. Okay. Suppose you have a graph, vertices V, edges E, then any subgraph can be formed by a deletion procedure. Delete certain vertices, delete certain edges. Similarly, if you start with a graph and you delete vertices and edges, you are left with a subgraph. The proof is pretty much immediate. Okay? If you have a graph and you remove some edges and vertices, as long as you still have a graph left over, you definitely have a subgraph. You have a subset and it's a graph. The deletion procedure made sure that when you delete an edge, no problem. When you delete a vertex, since you also delete the edges connected to it, you are definitely left with a legitimate graph. And very similarly, whatever subset you have, simply start from the original graph and remove the stuff that you don't want to keep. And that's how you can create a subgraph through deletion. There's also a notion of something called flattening a graph and simplifying a graph. So suppose you have directed graphs or multigraphs. They are definitely useful in certain contexts, but you might only be interested in which vertices are connected to which vertices, regardless of in what direction, or perhaps regardless of how many times. If you have a directed graph, and you just get rid of all the directions, replace all of the directed edges with undirected edges, producing a new graph that has the same vertices and edges, but is now undirected, that's called flattening. So a directed graph, you flatten it into an undirected graph. Alternatively, if you have a multigraph and any edge which is redundant, in other words, if any edge has sort of a backup, there are two edges connecting the same vertices and you simply remove one of the backups. If you keep doing that as much as you can, so that no vertices remain connected by more than a single edge, but you did not actually change which vertices are connected to each other, that's called simplifying. So flattening a graph is just removing direction from a directed graph. Simplifying is taking a multigraph and saying if there were multiple edges connecting these two vertices, just replace that with a single edge. If you have a directed multigraph, so you have both, simplifying the graph only involves removing redundant edges in a single direction. Okay, if you have directed edges and multiple edges, simplifying only removes redundancies that duplicate the same direction. So you might still have two edges connecting a vertex if those two edges go in each direction. So some examples of flattening and simplifying. Here's an original graph. It is a directed graph. If I flatten it, I simply replace all of the directed edges with undirected edges. Now I simplify. Anywhere that I saw multiple edges, I replace with a single edge. Here is a graph, okay? It is a directed multigraph. If I simplify it first, I look, are there any redundancies? Yeah, there are two vertices that go from C to B, so I replace that with a single one. Then I can flatten this graph, replace the directed edges with undirected ones. But maybe from the original, I flatten it first, replace all of the edges with undirected edges. And now I simplify it. There were three edges here, so now there's only one. There were two here, now there's only one. Notice that from the original, if I simplify and then flatten, versus from the original, if I flatten and then simplify, I might get different results. Flattening and simplifying are two different things, and it might matter what order you do them in. Next up, a notion called connected components of a graph. Suppose you have a graph, it's got vertex set V, edge set E, as is our typical notation, and now we have a subgraph, G prime. which is connected, is not the null graph, so it does actually have a vertex. And then G double prime is a connected subgraph of G. G prime is also a subgraph of G double prime, and from that you conclude G prime equals G double prime. So there's a lot of notation here, but we've got a graph G, a connected but not null graph, G prime, and then if you can find another connected subgraph that G prime is also a subgraph of, you must have found G prime. In other words, it's not possible to find another connected subgraph containing G prime without being all of G prime. G prime is then called a connected component of G. Now this definition is a little wonky, but visually it will make a lot of sense. So intuitively, a connected component is a subgraph that is connected and cannot be made into a bigger connected subgraph. So for example, suppose we have this graph here. Can you think of any subgraphs that are connected and cannot be extended into a different connected subgraph? There are three. There's this one, and that one. Okay. So this right here is a subgraph of the original. But back in the original, if I start with this, if I try to add any vertices or edges while still being a subgraph of the original, I'm not going to be connected. This is as big as I can be and still be connected. This is another subgraph that is as big as it can get while still being connected, and so is this. This is a connected graph. Every vertex is connected to itself for the trivial reason that H is just there. Okay, next up, bridges. Suppose G is a graph and E, lowercase e, is a certain edge on that graph. If deleting a single edge results in more connected components than you started with. Okay, so from the original graph, I have a certain quantity of connected components. I then delete an edge, and now I have more connected components. That's called a bridge. Equivalently, E is a bridge if there's a pair of vertices, Vi and Vj, not the same vertex, so that any path that contains those two vertices must contain exactly that edge E. It's the only edge connecting those two. Okay? And not only is it the only edge connecting those two, any way of getting from Vi to Vj must cross that edge. That's called a bridge. So in the graph below, try to identify which edges are bridges and which aren't. Think of, if I delete that edge and nothing else, does it break the graph into more pieces than it started with? If so, that's an edge. That's a bridge, sorry. So here's the graph. Which edges, if I deleted them, would cause the graph to have more connected components than it used to have? Well, the original graph has one connected component. It's already connected. So which edges, if I delete them, would cause a disconnection? These ones, okay? If I were to delete this edge, now this is disconnected from the rest. If, however, I was to delete this edge, this vertex would be disconnected. If I delete this edge, this whole subgraph would become disconnected. If I delete this edge, this whole subgraph becomes disconnected. If I delete this edge, this vertex becomes disconnected. This edge, however, is not a bridge. If I delete this edge, this vertex is still connected to everything it used to be. It just has to go sort of the long way around. Okay, the equivalent definition regarding up here, that you have a pair of vertices and only can get from one to the other by going across that edge. Think of these two vertices right here. If I want to get from this vertex to that one, my only choice is to go across this edge. If I want to go from this vertex to that one, my only choice is to go across this edge. This is not a bridge, because if I want to get from this vertex to this one, while I could take this edge, I could also go around it. Okay. So it's possible to get between these two vertices without taking this edge. It's not a bridge. All right, let's establish a theorem about connected graphs. If G is a connected graph and it has n vertices, it's not the null graph, it has at least one vertex, then G must have at least n minus 1 edges. In other words, if you want to make a connected graph, based on how many vertices you have, there's a lower bound on how many edges must be used. You can't make a connected graph with exceptionally few edges. We're going to prove this by induction on the number of vertices. Our base case is 1. Anytime you have a single vertex, that's connected. And it certainly has at least 0 edges. There's really not much to prove here. A single vertex hanging off by itself is connected to itself. And even if you had like a multigraph or something, it would certainly have at least 0 edges. We're not claiming that G has exactly n minus 1 edges, just at least. So if n equals 1, do you have at least 0 edges? Well, yes. Now inductively assume that there is an n, so that any connected graph on n or fewer vertices must have at least n minus 1 edges. We've made our inductive hypothesis. Now let's suppose we have a connected graph with n plus 1 vertices. We want to show it has at least n edges. Pick one of the vertices and delete it. Okay. Now I have n vertices, but possibly several connected components. If you delete a vertex from a graph, you might disconnect it. So let's suppose there are k connected components. Okay, if I delete the graph, if I delete one vertex from the graph and I create several connected components, we'll say there are k of them. There are n1 vertices in the first connected component through nk in the last. So this is the number of vertices in the first connected component, then add the second all the way up to the last one. All together, that's all the vertices except the one I deleted. Now each connected component has n or fewer vertices because I started with n plus 1 vertices and I deleted one. So each connected component can have at most the full n. Now we've assumed that any graph with up to n vertices which is connected must have at least ni minus 1 edges. Each connected component has ni vertices. It's a connected component, so it's connected. Therefore, it must have at least ni minus 1 edges. So the original graph was connected, and deleting one vertex made k connected components. What follows is I must have deleted at least k edges from the vertex we removed. That vertex must be connected to all of the connected components we created because the original graph was connected. So all of the connected components I now have had to be connected to the one vertex we deleted. Since I have k connected components that were all connected to the one vertex we deleted, that one vertex must have had at least k edges connected to it. So overall, the number of edges from our original graph must be at least the following. This is the number of edges in the first connected component, at least this many. The second connected component must have at least this many edges. All the way to the last connected component must have at least this many edges, and we deleted at least this many edges. So altogether, the number of edges is at least this much, but notice I have a minus 1 for each of my n's, and I have k of them. So I end up with a minus k, which exactly cancels that plus k. Then we have n1 plus n2 up to n sub k, which was assumed to be n. So the number of edges in our original graph must be at least n, which is exactly what we were trying to prove for our inductive proof. So any graph that is connected with n vertices must have at least n minus 1 edges. The contrapositive is useful. If you have a graph that has n vertices and has fewer than n minus 1 edges, it must be disconnected. What is the notion of k connectivity? Not just connected graphs, but k connected graphs. Well, it's nice to describe what graphs are connected and what aren't, but some graphs are more connected than others. There's more redundant connections between vertices. Okay, so on the left, this graph is somehow more connected than the one on the right, because on the right, there's a single vertex that's like a central hub. And if something were to happen to that vertex, all of a sudden there'd be disconnections. You can imagine vertices being like communications hubs, in which sort of cell towers are communicating with each other, something like that. In the picture on the right, if this cell tower goes down, then this region and this region are suddenly disconnected from each other. However, in this graph over here, you can see that even if I remove any single vertex, everything else is still connected to itself. So somehow the graph on the left is more connected than the graph on the right. So if a graph has the property that deleting k minus 1 vertices, no matter which k minus 1 you choose, still results in a connected graph, but there is a way to delete k vertices that produces a disconnected graph. That's called a k-connected graph. So the k in k-connected says, it's possible to delete this many and become disconnected, but if I delete any amount fewer than that, I am still connected. So the higher this number, it says if you want to disconnect the graph, you have to delete more vertices. Okay, so we also require the graph to not be complete to apply this definition. If you try to disconnect complete graphs, you kind of have to delete the entire thing. So we don't actually talk about k-connectivity when relating to complete graphs, but it's not that big of a deal. So the graph on the left, any single vertex I delete, the result is still connected. However, it's possible to delete 2 vertices. For example, if I remove vertex 2 and 3, then vertex 5 will be left by itself. So that's called 2 connected. Any one vertex will not suffice, but it is possible to pick 2 vertices to delete to make this disconnected. The graph on the right, however, is 1 connected. There is a single vertex, D, that if I delete that, creates a disconnected graph. So the higher the number in k-connected, the more vertices would be required to delete in order to disconnect it. And if you're trying to design some sort of network and you want it to be robust to failure of multiple components, you want a highly connected graph. All right, let's establish a theorem. Suppose k is any positive integer, and we have a simple graph with at least k plus 1 vertices, and it is k-connected. Then every vertex must have degree at least k. So we're using the same k in a lot of places. I have at least k plus 1 vertices, and I am k-connected. Then every vertex must have at least degree k. This requirement on having sufficiently many vertices is not usually the issue. Basically, this is saying if you have a k-connected graph, every vertex must have degree at least k. So proof, suppose we have a simple graph. It has at least k plus 1 vertices, and one vertex has degree smaller than k. What we're going to do is show that that graph is not k-connected. What we do is we delete every vertex connected to that one. This vertex has degree smaller than k, so there are fewer than k edges leaving it. At most, k minus 1. If I delete all the vertices connected to that one, I've deleted at most k minus 1 vertices. Okay, the graph was connected to at most k minus 1 vertices, delete all of them. We've deleted everything connected to that vertex, so this is no longer connected to anything else. But since the total number of vertices was at least k plus 1, and the most we could have deleted was this k minus 1, there are at least 2 vertices remaining. So the one vertex that I disconnected is actually disconnected from something else. There is another vertex left other than this special one. So specifically, we took our vertex of low degree, deleted everything connected to it, and there was still at least something left over. Since we disconnected our graph by removing at most k minus 1 vertices, the graph is not k-connected. It might be k minus 1 connected or k minus 2 connected, but it's not k connected because I was able to remove less than k vertices and produce something disconnected. And what this tells us is if you want to produce something that's k connected, every vertex has to have at least that degree, as long as you have a sufficient quantity of vertices. So if you want to make a network that is robust against failure of multiple devices, you need a lot of edges. If you want to make something, for example, that the failure of any 3 nodes does not cause any disconnections, then you want something that is at least 4 connected, possibly even more. But if you want a graph to be 4 connected, every degree is going to need to have degree, every vertex is going to need to have degree at least 4. And that, in a large graph, is going to be a lot of edges to put down. And in the real world, edges would be things like laying a fiber optic cable. Every edge has cost. So making something that is highly connected could be very expensive.